Nick Daniels, the president of Purdue University. Yeah. Did you see Purdue and lots of other schools have canceled spring break?
Really?
Yeah. So they're not going to have any spring break.
Well, most schools are coming home over Thanksgiving.
Right. Oh yeah. Right. 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 So they'll come home like I think a little bit earlier. So they're going to change the schedule. Right? Wouldn't that be a bummer, man? You finally get to college. No spring. Yeah, we have a huge fall break. It is October 21st. So I forget if you guys, because we have that Monday and Tuesday, we have parent-teacher conferences. I do not know if you have to go those days. I think you do. I think that Monday and Tuesday you go. They switched it up this year.
Yeah, we get Wednesday, Thursday, Friday.
Wednesday, Thursday, but we all get Wednesday, Thursday, Friday off. So yeah, it's really nice. All right, so let's talk. Global climates and biomes. This is a weirdie because they put these two things together. I don't know why they do it, but they do. And so if you want to take a few notes, you can today. We're gonna watch some videos, but we're also gonna hopefully go outside in a few minutes, and we're gonna play with my little globe here. So this is chapter 4. Okay, and I used to hate this chapter. It used to drive me crazy because, well, A, I didn't know much about it, and then B, I got it. Okay, for a lot of different reasons. Okay, but oh, hi there. That came out of nowhere. Emma, was it you, Emma? Gilly, was it you, Gilly? That's like a perfect Gilly moment right there, right? I have my back turned. There's a piece of paper. Was it you, Gilly? Oh man, I'm so glad you said it. All right, just shut up, Emma. All right, now, so people get themselves into trouble, especially when they talk about climate change, because they're talking mostly about weather. Okay, and there was a guy a couple years ago. Like, remember we had those like negative 35-degree weathers, right? Okay, we were out of school for like a month. Remember that? It was crazy. I mean, it kind of got cold. Was it 2 years ago? I'm talking about like maybe it was 4 years ago. Like it was so bad. Like we were under a state of emergency. You were not even allowed to drive unless you were like, paramedic, or you were forced to go to work, that kind of stuff. I remember bundling up and walking to CVS, and it was just like we were living in the Arctic. It's that polar vortex, right? Remember the polar vortex? We had a little polar vortex last year, but not like that anymore. Okay, and there was a guy that worked for the Indiana Department of Environmental Management. Okay, and he tweeted out like, something like so much for climate change, right? Okay, the globe is not getting warmer. Okay, these negative 35-degree temps are proof that all these climate scientists are just full of crap. Okay, and then he came under some trouble or whatever. But what he was talking about was weather. Okay, right? Weather is the day-to-day. Climate is the long-term average conditions. Okay, so when we're talking about like our climate here in Indiana, we're talking about a specific maybe biome like temperate deciduous forest. That's our major biome here in Indiana, and the average temperatures and the average precipitations over a long period of time. Yes, there's sometimes we get more rain. Yes, there are sometimes we get less rain, right? We experience the drought conditions. And we definitely had weird rain this summer. Remember 2 summers ago, people were like, are farmers even going to be able to plant anything? Like farmers didn't start planting until like June. Remember this? It was insane, right? And so I remember there was that window. They're like, if we can't plant by this date, there's no way we can do it, right? Okay, we've got those weird anomalies. That's weather, right? Climate is the long-term average conditions. And soon we're going to talk about a real weird, and it's tough to kind of understand, but it's called El Nino. Have you heard of El Nino?
It was like the El Nino.
Yeah.
Yeah, so it's saying the boy.
Oh yeah. Who said that? I did.
No, it's in the book.
It's in the book. The El Nino. Huh, that's interesting. I'll have to ask the author. um, why I do that. Okay, so you don't have to write these things down, okay? And I'm gonna tell you something inappropriate here in a second. Okay, but the two biggest areas that we're gonna focus on for us and when it comes to environmental science is the troposphere and the stratosphere. Okay, we talk about these, because all the weather occurs in the troposphere. I don't have any, but I have those, that tissue in the back. Right? Yeah, I'm sorry. I'm fresh out. Okay, and the stratosphere is right above that. Okay, so the troposphere where all the weather occurs. Okay, and the stratosphere is right above that. Now you're also going to hear me talk about stratospheric ozone, and you're going to hear me talk about tropospheric ozone. Okay, one is good and one is bad. Well, which one do you think? Which one do you think is a good one? Tropospheric ozone or stratospheric ozone? Stratosphere is the good one. Troposphere is the bad one. And ozone is in our immediate presence. It's in the form of smog. Okay, anybody ever been to California? Okay, it is nuts. Troposphere is bad ozone. Stratosphere is good ozone. Okay, so when we talk about, let me pin this right here. When we talk about the stratosphere ozone, that's really, really good. Okay, in fact, if we didn't have the stratospheric ozone, we'd all be dead. Why?
There would be anything to keep the.
I like how you trailed off there. You were going real good, and you're like, well, I don't know what I'm talking about here. Right? No, you got it, Addison. What is it? Yeah, so solar radiation. Okay, those UVB rays, UVC rays, if they get down through the atmosphere and they get on our skin, what happens to our skin? Yeah, we get skin cancer, right? In fact, there is a hole in the ozone layer. We'll talk more about that later. It's shrinking, thankfully, but it was all thanks to our stupid hairspray in the 80s. You ever see pictures of your parents in the 80s, man? You see the hair? Okay, yeah, I'm assuming most of your parents are probably like 80s parents, right? You know, your moms ever do like the glamour shots? You guys know about glamour shots? No, yeah. Who said yeah? Okay, good. Glamour. Did your mom get one? Oh yeah. It was in the mall, but they do you all up, make you look like you're like a Hollywood star, but it was ridiculous. Google glamour shots at some point, and you'll get some cool pictures. All right, so here's the inappropriate thing. Okay, but it stuck with me for a really long time. Okay, so our layers of the atmosphere are troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Okay, yep. You need to know the order in which they exist, and here's how I want you to remember them. Okay, this comes from Tom Narrigan. Okay, don't write this down. You won't need to. You'll remember it. Okay, Tom Narrigan, probably one of the smartest students I've ever had in my life. Tom, I hope you're doing good if you're watching from home, which he's not. But his research, we'll zoom in with him this year. His research is about these ants and how ants basically get other ants to do stuff for them thanks to these like little sex glands. It's crazy. Like his work is nuts. But anyways, he's genius. So he came up with this. I'm not sure why. So here you go. Tom sucks my tiny erection. I don't know why it is stuck with me. I will never ever forget it as long as I live. In fact, I love it when if you guys all take the, hopefully fingers crossed, take the AP exam in person. Like kids will come back and they said, oh, I automatically knew when so-and-so was on question 18 because I heard the giggles because it was Tom sucking my tiny erection, right? And so nobody ever misses those questions, and I guarantee it'll be on there. So troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Those are the layers. I'm not too concerned about the temperature. Temperature gets kind of crazy, okay? Like temperature decreases, increases, decreases, then it gets really hot, okay, up there in the thermosphere, right? Okay, so, up in the stratosphere in space. All right. So there is unequal heating of the Earth, okay, and that's thanks to the seasons, right? And thanks to this tilt, okay. I want you to know the term albedo. Don't confuse that with libido. Completely or albino. Completely different terms altogether. Okay. What's what? Oh, exosphere. Sorry, exosphere. Okay, so let's talk about albedo for a minute, and hopefully this is not a tough concept, but sometimes people are like, no, I'm not quite understanding this. All right, let's take a look at this picture. Okay, we got this nice bright sun, and the sun is sending all of its photons down. Okay, and sometimes those photons are reflected back up into the atmosphere, and sometimes they're absorbed. But notice that all of them are bouncing back up, right? Okay, so all these photons, and this trips me out a lot. Okay, so when photons come down, okay, and let's say they hit a rock in this room, this rock, boom, okay, hit this rock. Okay, if this was out in the sun, okay, I would know that photons are hitting this. After a while, how would I know that? It gets hot, right? Okay, but then it gets cool, right? Why does it get cool? Because the photons are being released from the rock. Okay, that's a weird thing to me, right? I have a hard. So it's absorbing some stuff, and then it's reflecting some stuff. But sometimes it's going to be really absorbed. And notice which one has what's the common thing of like what has a high albedo and what has a low albedo? Like what's the commonality between all the higher numbers and then all the lower numbers? Okay, higher, well, they're all reflecting a little bit, right? But what do the higher numbers have in common? They have, okay, maybe something to do with water. Maybe if I kill this light. Okay, there is maybe some water there. Definitely has something to do with water. Okay, yeah, Emily. Yeah, it's the color. Okay, what color is all those things with the higher albedos? They're lighter colors. Okay, if we go outside, okay, right now, and I take a temperature gun and shoot it on Logan, okay, and I'm gonna shoot it on Justice, who's gonna be hotter? Yeah, why? Okay, why is he gonna be hotter? He's got a black shirt, right? Okay, Logan's got the white shirt, right? And so that temperature, what happens when you wear dark clothing on a hot day? The heat absorbs into that black shirt, right? The white shirt reflects that, and so boom, that's got a higher albedo. Y'all with me on this? Walmart is doing something interesting at all of their stores now. I think every Walmart now has completed this. I don't know that 100% for sure, but they want to cut down costs, okay? Not necessarily to save you money, but to save them money. And so they did something to their buildings, okay, more specifically to their roofs, to cut down on energy costs. You may know what Walmart did to their roofs? Painted them white. So yeah, all of Walmart's roofs are white, okay, and why is that? Because the heat reflects back up, right? Pretty cool idea. Why didn't we think about that a long time ago? Okay, there you go. All right, let's look at, okay, so I basically said some of those things. All right, so let's talk about these convection currents. Okay, so we all know the wind is blowing. You guys ever see this really cool app? Let me go to, you can get this as an app on your phone, and I really love it. But it's also, why can't I spell? I think it's windy.com. Let's go to this. Yeah, here it is. So this shows all these different wind patterns, and we have this nice hurricane over here. okay, which is pretty exciting. Hurricane Teddy, look out, Teddy's coming to get you. But let's go zoom in on North Manchester. There we go, and hopefully it'll zoom in, and it'll show at this point that all of our wind is coming from the southeast. Okay, and it'll tell you all those different things. The wind is in. I need to switch this and make it miles per hour to make that a little bit more. Let me log in. Hopefully that'll do it. Save my settings. Yeah, so 6 miles per hour right now, so not too incredibly windy. Okay, is that typically where our wind is coming from the southeast? No. Where's it typically coming from?
West.
It's from the west, right? How do we have wind, by the way? Do you know what happens?
God, blowing his nose.
Oh, wow, I like that. Yeah. The what? Yeah, it's a lot about heat, right? For sure. Okay, and all right. So let's look at density. Okay, so less dense air rises. Okay, denser air sinks, and that's going to be important. So a lot of these terms I just kind of want to establish them, and then we'll come back to them when we talk about some of these wind currents. Okay, I think I told you before that our number one greenhouse gas on the planet is water vapor. Okay, and so we would be in big trouble. Our number one anthropogenic greenhouse gas is CO2. Okay, so when we talk about climate change, we talk about CO2, but really, the number one greenhouse gas is water vapor. Okay, it has a higher capacity. Warm air has a higher capacity for water vapor than colder air. Okay, so when we have warm air, it's going to be like more kind of humid, right? Okay, you don't really say in the dead of December, like, oh man, it's really sticky outside, right? Okay, so that warmer air has that higher, it's going to have a higher water vapor capacity. I like this word, adiabatic heating or cooling. Okay, so this is that idea of what happens as air rises and or as it sinks. So when air rises, pressure decreases, okay, and the air expands. It's kind of trippy, okay? The other way around, when air sinks, the pressure increases and air decreases in volume, okay? And then finally, latent heat release. When water vapor in the atmosphere condenses into liquid water, energy is released. Sorry, into liquid water and energy is released. Okay, and again, if these terms are like, nah, okay, we're going to come back to all this stuff, and hopefully it'll all make sense when we talk about these weather patterns. Okay, but all about these convection currents. Okay, so where are things moving? We know right now we've got some air currents moving towards us. Okay, so we've got the equator. Okay, so I'm going to get out my my little globe here. And here's the equator. Sorry, I want to make sure you can see equator. And then I've got 30 degrees north and 30 degrees south. We call that the Tropic of Cancer and the Tropic of Capricorn. Okay, we'll get to that later. Okay, but hopefully you can all see my globe, and I'll if I keep talking, Mags, and you're like, I need to see this sort of stuff, just yell at me, okay? All right, we are located right here on this X, and you can see I've drawn this kind of weird blue line that kind of goes up and around. That's our jet stream, right? You guys have all heard of the jet stream before, right? So if the jet stream, if I got my finger on Indiana right here, and the jet stream goes down like this, what's our weather like? Okay, when the jet stream goes down underneath my finger, it's colder, right? Why is it colder? Yeah, it's coming from the north. That nice northern air creeps down and it makes us cold. If the jet stream's above Indiana, where's our weather coming from? Yeah, it's coming up from the south, right? So I get the warmer kind of Floridian weather, right? So when we had that polar vortex, that jet stream was much, much lower. Okay, so what about the equator? Why is it so special? Okay, well, the sun heats that, nicely year round. Okay, so you're always going to have this weather. Okay, so I want you to see my fingers kind of going up like this. Okay, so for the purposes here on Hadley cells, here's what happens. We're at the Tropic of Cancer and the Tropic of Capricorn, and the currents go up like this, and it heats up. When it heats, okay, the air evaporates, right? Okay, up, but then that's also where it's going to condense and rain. Okay, so if you go to a tropical area, you're going to have rain every single day, and it's going to be about the same temperature every day. Okay, so all of these currents are flowing towards the equator. Things are going to heat up, and then it's going to rain, and the air condenses and cools, and then heads back down to the Tropic of Capricorn. Okay, and Cancer. So this happens like not just here, but like all around the equator. Okay, so if I could do this all the way around, right? It's not just one spot. This is going all the way around. Does that make sense? On every part of the equator, okay? Things like move to that hot area, okay? They evaporate, they condense, it rains, okay? All the way around in between the Tropic of Capricorn or Cancer and the Tropic of Cancer, or Capricorn, sorry. All right, that's what a Hadley cell is. Okay, so I don't know. I like this diagram because it shows basically there's the heat. Okay, and this is called the ITCC, is the intertropic convergence zone. Okay, so everything's converging together along this line in the equator. Okay, the rising air, okay, experiences cooling, causes that water vapor to condense and have rain. Okay, so there's that adiabatic cooling. Okay, that condensation of water produces a heat release. Air expands further into the atmosphere, so it's drier and colder up here. Okay, but then that warm air rising displaces the cooler air. Okay, that air sinks. Okay, and it reaches the surface as warm, dry air, and then flows back towards the equator. Okay, so it's real trippy because here's like going up, right? You got this dry, cold air. Okay, that dry air kind of comes down into hot air, then the hot air kind of comes back, and the whole cycle starts all over again. That's called a Hadley cell. Any questions about that? Thanks for sticking with me. I know this isn't the most exciting. I just said all of those things. All right. So let's talk about the Coriolis effect. And I'm going to throw a ball at you, and then let me just still touch the ball. Okay. If it hits you, I'll spray your face off or something like that. Okay. All right. So the Coriolis effect is something trippy. Okay. Let's go on a quick field trip. Okay. Can you mask up real quickly?
I guess so.
We're gonna debunk. I'll be right back, Maggie. Okay. So I'll tell you about where we're going in just a second. Come with me.
You're taking a picture of the outside. What if I wear my pants like this, Trina? What? What if I wear my pants like this? Do it. Unnecessary. Like the wrestlers? Do it. I don't care. Where's Elijah? Elijah, look, I'm you now.
Yeah, only wrestlers can do that, bro.
I didn't be rude.
I do, that bathroom is somewhat of a bummer because there's no separators in between the urinals, right? Kind of awkward. So we just went to the bathroom. Sorry about that. You missed that. Maybe you're glad that we didn't miss it. But we looked at the flushing toilet. Okay, so the reason why we're talking about this is because we're in the northern hemisphere. Okay, and so there's this little rumor that like if you're in the northern hemisphere and you flush a toilet, it's going to spin to the right, then down into the hole. We did observe that. If we were in the southern hemisphere, that the toilet water was going to flush to the left because of this Coriolis effect. And is that true or not? Let's take a minute to actually look at two cheesy little videos, but I like them because they helped me learn more about the Coriolis effect. And so here's the first one.
Coriolis effect. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth, but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels.
Okay, so notice that's to the right, okay? So what? Why do we need to know this? No.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is because it's closer to the equator. That means that the paper airplane is spinning faster as well. And when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high pressure air surrounding the center or eye of a storm is constantly rushing toward the low pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction.
Does that make sense, folks? All right. Thanks for sticking with me today.
Will we talk about the other cycle tomorrow?
Yep. The Milankovitch? Yeah. It's super confusing. But I hope it'll make sense.